Snow, with its white and soft mantle, transforms the landscape into an enchanted, almost fairy tale-like scene. The world seems wrapped in a muffled silence where every sound is dampened and every movement slowed down, creating a surreal atmosphere. The roofs of houses are covered with a pristine layer, trees bend under the weight of the snow, and the streets turn into immaculate paths. This spectacle has fascinated humankind for centuries, evoking deep emotions, nostalgia, wonder, and reflection. But beyond its beauty and charm, snow represents an extraordinarily complex physical phenomenon, governed by principles of chemistry, thermodynamics, and atmospheric physics. Its formation depends on a delicate balance between temperature, pressure, and humidity, and each individual snowflake tells the story of the atmospheric conditions that generated it. Each snowflake is a masterpiece of nature, a microcosm of symmetry and delicacy. However, the reason why snowflakes always take on a hexagonal shape has intrigued scientists and philosophers for centuries. The answer to this question takes us back in time, to the era of Johannes Kepler, and pushes us to explore the secrets of crystallization, even questioning whether similar phenomena could exist on other planets. It was the winter of 1611, and Johannes Kepler was walking through the streets of Prague, more precisely on Charles Bridge. During his walk, a snowflake landed on his coat. The astronomer noticed its perfect hexagonal symmetry and, fascinated by the phenomenon, posed a seemingly simple but profoundly significant question. Why do snowflakes always have 6 sides? Thus was born the treatise De Neve Sexangula on the 6-cornered snowflake, one of the first scientific works dedicated to the structure of snow. Kepler realized that the shape of snowflakes did not depend on the material they were made of, water vapor, but on how their particles arranged themselves during crystallization. He hypothesized that snow crystals were formed by microscopic spheres arranged in the most efficient configuration to occupy space, a hexagonal structure. This hypothesis led to Kepler's conjecture, which states that the densest and most efficient packing of equal spheres is precisely the hexagonal one. This idea would have profound repercussions in mathematics and physics, influencing even the study of atomic arrangement in crystalline solids. For Kepler, the snowflake was an example of the geometric order of the universe, proof that the cosmos itself follows harmonic and precise laws. His love for geometry was reflected in every aspect of his work, including the search for a missing planet between Mars and Jupiter, which we now know as the asteroid belt. Over the centuries, science has deepened Kepler's insights, confirming that the hexagonal shape of snow is the result of the molecular structure of ice. The most common type of ice on Earth, called ice-ich, has a hexagonal crystalline arrangement. When water vapor in the atmosphere cools and condenses directly into ice, the water molecules organize themselves into a network that reflects this geometry, giving rise to snowflakes with 6 arms. In the 1930s, the Japanese physicist and glaciologist Ukichiro Nakaya extensively studied the formation of snow, cataloging its different morphologies and recreating its growth in the laboratory. He discovered that the shape of snow crystals primarily depends on 2 factors. 1. Temperature. 2. Supersaturation, the amount of water vapor available in the air. Depending on these variables, snowflakes can take different shapes, such as flat hexagons, thin needles, or complex dendritic structures. Nakaya's diagram, which relates temperature and humidity to snow shape, remains a fundamental reference in glaciology to this day. Despite scientific advancements, the formation of snowflakes remains an incredibly complex phenomenon. Even knowing the initial conditions, it is almost impossible to predict the exact final shape of a flake. This is because crystal growth follows chaotic dynamics, influenced by microscopic variations in pressure, humidity, and temperature. In scientific terms, it is a many-body system, where numerous particles interact according to non-linear physical laws. This makes every snowflake unique, even though they all respect the same hexagonal symmetry. If on Earth, snow is the result of the crystallization of water, similar processes could occur on other planets or moons with different materials. For example, Mars experiences weak snowfalls of solid carbon dioxide, dry ice, in the polar regions, especially during the Martian winter. Titan, Saturn's moon, has an atmosphere rich in methane and ethane, and could experience precipitation in the form of organic snow. Europa, Jupiter's moon, has a subsurface ocean beneath a thick ice crust, and could have snow composed of frozen water crystals. Pluto shows signs of frozen nitrogen precipitation, covering its mountains and the plains of Sputnik Planitia. Each planetary environment has different conditions, and the snow forming on these celestial bodies would not be identical to Earth's. But the principle behind crystallization remains the same. Molecules organize themselves into the most stable and efficient structure according to local conditions. Snow, seemingly simple and common, is actually an extraordinary phenomenon that unites science, mathematics, and natural beauty. From Kepler's insights to modern research, the journey to understanding snow has revealed fundamental laws of physics and the universe. But the study of snow is not limited to Earth. Its presence on other planets could offer new perspectives for better understanding the atmosphere and climate of distant worlds. The fascination of snow, therefore, lies not only in its aesthetics, but also in the mysteries it still holds and the questions it continues to raise. Thank you for watching. Leave a like and subscribe to the channel to not miss the next videos.